You know what's really fascinating about this paper? The elegant way they implemented the proof search tracing using monads.
Oh no, monads. We just started learning about them in my functional programming class, and honestly, all that category theory stuff makes my head spin.
Hello, everyone, and welcome to the very first episode of United Reasoning. I'm Justin, coming to you on this chilly December 1st, 2024, from Prague, where I'm joined by Hana in our cozy office, and we have Aaliya joining us online from sunny India. Today, we're kicking off our paper review series with a fascinating paper about making theorem proving more accessible.
Yes, and I'm really glad we're indoors. It's freezing outside. But this paper really warmed me up to some cool ideas about proof automation.
Hi everyone! While you're dealing with winter, we're having perfect weather here in Bangalore. I'm excited to discuss this paper since I've been studying theorem proving basics in my undergraduate program.
Perfect. Let's start with the basics. This paper introduces PSL, a proof strategy language for Isabelle/AUL. The key idea is to make interactive theorem proving less tedious and more accessible to newcomers.
Right. You know how usually we have to manually guide the theorem, prover step by step? PSL lets us write high-level strategies instead, kind of like telling it, try induction, and then simplify, rather than specifying every little detail.
Ooh, that sounds interesting. But what exactly does it do differently from regular theorem provers?
Great question. PSL takes what we call a meta-tool approach. It's quite clever because it brings together different proof tools under one roof. Traditional proof tactics, counterexample finders like QuickCheck, and even Sledgehammer, which is itself a meta-tool.
And what's really neat is that you can write your own proof strategies in PSL since it's provided as a language. Plus, it supports parallel proof search with special combinators, so if you have a multi-core machine, it can try different proof approaches simultaneously.
That sounds powerful, but how does it actually work in practice?
Well, instead of you trying hundreds of different combinations of tactics manually, you write a high-level strategy, and PSL automatically explores many possibilities to find a working proof. You can even tell it to try different approaches in parallel if you want.
Does it actually work well in practice? I'd love to see some numbers.
The results are quite impressive, actually. In their evaluation, given 300 seconds per proof goal, PSL's default strategy, called try_hard, solved 1,115 out of 1,526 proof goals, while Sledgehammer, a popular existing tool, found proofs for 901 goals.
And get this, 299 goals, that's about 20% of all goals, could only be solved by PSL's try_hard strategy. Pretty impressive, right?
That does sound impressive, but surely there must be some limitations.
Absolutely. The paper is quite honest about the limitations. For instance, the search process can be quite time-consuming, though they mitigate this by making it memory efficient so you can let it run for hours.
Yes, and in some specific cases, 3 out of 35 theories they tested, try_hard actually performed worse than Sledgehammer. This happened mainly when the problems were particularly well-suited for Sledgehammer's approach.
What makes PSL particularly good at certain types of problems?
PSL shines in 4 main areas: mathematical induction or co-induction, type class mechanisms, specialized tactics, and general simplification rules. It's also better at handling what they call the hidden fact problem.
The hidden fact problem?
Oh, let me explain what this hidden fact problem is. It's actually quite interesting. You see, when you're trying to prove something, sometimes the lemmas that would be really useful for your proof are kind of hidden inside the definitions of other facts. The relevance filter in tools like Sledgehammer has a hard time finding these because they're not immediately visible.
Could you give an example to make it clearer?
Sure. Think of it this way. Sometimes you need to first massage your proof obligation by applying some rewriting or simplification before these hidden facts become visible to the relevance filter. PSL is clever about this. It can use strategies that first apply some automatic simplification to reveal these hidden facts before trying to use them in the proof.
Exactly. And PSL even has a specific strategy pattern for this. You can write something like auto, then repeatedly try hammer, then check if it's solved. This way, it first simplifies the problem to expose those hidden facts before attempting the proof.
You know what's really fascinating about this paper? The elegant way they implemented the proof search tracing using monads.
Oh no, monads. We just started learning about them in my functional programming class, and honestly, all that category theory stuff makes my head spin. Sometimes I wonder if we really need all this abstract mathematical complexity.
I felt exactly the same way when I first encountered monads, Aaliya. But this paper actually shows a really practical use case. You see, when implementing a complex proof search system, you need to handle things like backtracking and keeping track of successful proof attempts. This could get really messy with traditional programming approaches.
Exactly. Instead of using references or pointers, which would make the code messy, or building an explicit search tree that would use too much memory, they used monads to represent the search procedure in a clean, functional way.
Okay, but could you explain how that works in simpler terms? Because right now in class, all I see are these abstract diagrams with arrows, and I'm having trouble connecting it to actual programming problems.
Think of it this way. They implemented something called a monad with 0 and plus that has 4 basic operations. The most important one is bind, which lets them chain proof steps together while handling all the complexity of backtracking behind the scenes.
And what's really elegant is how they implemented it using lazy sequences. The bind operation basically applies a proof step to many intermediate states and concatenates the results, exactly what you want for backtracking search.
Oh, I think I see. So instead of manually managing all the different proof paths, the monad structure handles that automatically?
Precisely. And they implemented this in standard ML, which is Isabelle's implementation language. Even though ML doesn't have native support for monads like Haskell does, they cleverly used ML's module system to make it work.
The really cool part is how this matches perfectly with Isabelle's normal execution model. The then and append operations for combining tactics are basically just monad operations in disguise.
That's fascinating. So they managed to make the implementation both clean and efficient at the same time. But I'm curious, how does this help with memory usage?
Good question. Because they used lazy sequences, the system can remove failed proof attempts as soon as it backtracks. This means it doesn't need to keep the entire search tree in memory.
Yes, and this is crucial when you're running proof searches that might take hours. You don't want your memory usage growing indefinitely.
That makes sense. In my programming projects, memory management is always a challenge when dealing with large search spaces.
Indeed. And this monadic approach also made it easier to implement the proof script generation feature. When a proof is found, they can easily trace back through the successful steps to generate clean, efficient proof scripts.
This all sounds really useful for beginners like me. How would someone get started with PSL?
The good news is that PSL is integrated into Isabelle/HOL's standard editor, Jedit. You just import the relevant theory files and you can start using it. They've made it very user-friendly.
And the best part is that the proof scripts it generates are independent of PSL, so you can maintain them without needing PSL afterward.
I can't wait to try this when I come to Prague for my internship. Though maybe I should pack some warm clothes first.
Definitely pack warm clothes. But yes, this tool really helps bridge the gap between novice and expert users of Theorem provers.
Speaking of which, should we wrap up with the main takeaways for our listeners?
Good idea. The key message is that PSL makes Theorem proving more accessible by allowing high-level strategies instead of detailed manual proofs. It's like having an expert assistant who can try thousands of possibilities for you.
And it seems to work really well in practice, with impressive success rates in their evaluation.
Before we wrap up, I should mention that if you're interested in learning more about PSL, the official paper is published in Springer's Proceedings, though that might be behind a paywall.
Oh yes, and there's good news for students. You can find almost the same version of the paper for free on ArgZiv. The preprint has all the important details you need to understand PSL.
That's really helpful. I'll definitely check out the preprint version since I don't have access to Springer from my university yet.
Exactly. And that brings us to the end of today's episode of United Reasoning. Thanks for joining us, everyone. Special thanks to Aaliya for staying up late in India to join us.
Yes, thank you all for listening. Stay warm out there.
Goodbye, everyone.